Thank you for the invitation. This is really a talk about Macaulay, and I really have to say this at the start, that I couldn't have begun to prepare this talk had David Eisenberg not educated me in this part of commutative algebra as we tried to write a book, which I think will come out this year, on Macaulay, his papers, Macaulay's book. What's correct in this talk is thanks to David, and all the mistakes are mine. In order to make this a comprehensible talk, some of what I'm going to say is not entirely true. Okay, some of the maths is a little simplified because the details get very complicated. For example, we will talk about points in general position, proving that these points will always be in general position turned out apparently to be very hard. If you wonder what I mean by an ideal, well, here's a nice simple one. The homogeneous functions generated by, polynomial functions generated by x squared and y, for example. David and I decided to call this thing an ideal because that's what it looks like in modern terms. These guys called it a module. If we called it a module, okay, it would confuse the modern reader, but would be historically accurate. We decided not to confuse the modern reader at some cost to the chain of words in the story. Okay, so sorry about that if that's what you want to hang on to. Okay, so Macaulay was born in 1862. He dies 2 days short of his 75th birthday in 1937. And I will talk about these different things. Don't worry, you don't have to write any of this down. His early work, which is in the sphere of mathematics, very much under the influence of Max Noether, and which Macaulay is working on until he goes to the ICM in 1904. This has a very important theorem, Noether's fundamental theorem. It fails in higher dimensions than the plane. We'll come to that. And the big person here for the breakthrough is Emanuel Lasker. It takes Macaulay quite some time to respond, maybe a decade, and he introduces the lasting concepts of perfect ideals. I'll try and say what that is. It's a difficult concept. Unmixedness, not so bad, and things called principal systems. Okay, a brief nod at his final papers, and then some discussion of the legacy. Now, this is the man of the hour. It's about the only picture we have of him, and it comes from St. Paul's School, where he was one of the mathematics teachers. That's a little story in itself that we'll come to. And the woman of the hour is Charlotte Angus Scott, who passed through Cambridge a bit before Macaulay did, and unable to get a research position in England, went and became a founding professor at the University of Bryn Mawr, where she remained, and was a great help to Macaulay in his early years. So these are the people we're talking about. Macaulay himself passed through Cambridge. He graduated 8th in 1882 in this ranking they had and still have. He joined the London Mathematical Society a bit later. This is a sign that he's thinking of going into research. And he starts in 1890 with his papers, 1895, sorry, and writes a string of papers, rather long, complicated attempts to get hold of the fundamental work of Max Noether in circumstances that Noether seems to have glossed over a bit. And he's in correspondence with Charlotte Angus Scott. She's very encouraging. And he has a result, a really good result, which I'll try and explain in due course, called the one set point. This is news to me when I started in on Macaulay. I'm not imagining anybody, unless you are experts in this stuff, I've ever met the one set point. And the other person we should look at, acknowledge the existence of, is Max Noether himself. And this wonderful quote from van der Waals that algebraic geometry was created by Max Noether. And then he goes on to say, that's to say he had a very stimulating intuition, but the details were often not entirely correct. I don't think Noether realized that they weren't entirely correct, but they certainly were rather vague round the edges. The big theorem here that it shapes the field in a way, and I won't talk much about, famous to this day, rewritten and expanded on many times since, is the Riemann-Roch theorem. Riemann is Riemann, of course. Roch was a young colleague and student of his. And it says that if you have an algebraic curve defined by a polynomial in two variables, let's call it a Riemann surface, of a certain genus, we can think about what that might be, and you specify a certain number of points on it, d points on it. And then you have a couple of spaces of things to look at. One is the dimension of the space of meromorphic functions having poles at these d points and no higher multiplicities, and therefore in particular nowhere else. And this is a space of functions. It has a finite dimension. You also have the space of holomorphic one-forms, things you integrate on the Riemann surface, and they will have zeros at these d points and of no higher multiplicity. And so you have this space, it has a dimension. You take these two dimensions, you subtract the one from the other, and you get a number, d plus 1 minus g. Okay, so that's the Riemann-Roch theorem. One-forms. One-forms were thought to look like this. You have your function f, the polynomial in two variables, and you write down an expression like this, where the function on the top, phi, is of degree no more than n minus 3 if f is of degree n. Okay? If you, for example, took the function w squared equals a cubic in z, you would be constrained to have just numbers up top for phi, and you would get an elliptic integral to play with, okay, the classical case. And you have a dimension of the space of these things. You just count the number of coefficients in an expression like this and take the ratio of them. Okay, so this is, in Riemann's language, something which is locally a surface. You can do complex function theory on it. It's really some kind of branched covering of the Riemann sphere. And Klebsch, and then Noether and Brillen came along as well, didn't like this at all. And they said, look, you know, Weierstrass has complained that this is all just hopelessly vague. So they said, you're studying a polynomial in two variables. So it's a plane curve, the curve in the plane. Probably, I would say that they're undeniably dealing with complex stuff by now. They are pretty clear that it's projective. Whether they fully understand the implications of that is a story. Anyway, we're going to study, they say, plane algebraic curves, complex curves in the complex plane. And Klebsch had found a formula for the genus of this thing. It's the formula you can see, well, you can see it, but there, this thing here for the genus, where n is the degree of the polynomial you've got, and delta and rho are the number of double points on the curve, and the number of cusps, okay? And it's, in fact, a birational invariant. Well, if you look at this thing and you let n increase, forget about delta and rho for a minute, you just let n increase, the numbers you get are 0, 1, 3, 6. You get the triangular numbers. So anything that isn't a triangular number the curve like that must have some singular points on it. Okay, so singular points are unavoidable. Okay, that's the first thing you notice. Now, how do these people handle it? They can't say, oh, there's a bunch of points. What they have to say is that you have the curve in the plane and you cut it by another curve. Two curves meet in a set of points. That's how you specify the points. That's how you get the functions that vanish at those points, for example, because these functions are polynomials in two variables. They define a curve. They have common zeros with the curve you began with. There you are. You've got two curves now, the one you're interested in, and some curves passing through, and a curve passing through the curve you're interested in the points you want. And you can look at the space of all of those curves that pass through the points you want. Okay. The trouble is, by Bezout's theorem, most likely any of these new curves will meet the curve you're interested in the points you're interested in, and some other points, right? Because Bezout's theorem tells you how many points there will be in an intersection like this. So that has to be handled, and I'm not going to talk about how that was done, but it's an issue. I'll explain just a little bit about why it's a rather unexpected issue. So you start off with the Riemann-Roch theorem. It's about points on a curve and some functions that vanish, or some one-forms, or whatever. And now you're talking about families of curves through those points, okay? And these families of curves have dimensions, and you would hope to count those dimensions by looking at the available constants you've got left after you've specified enough constants to insist that your new curve passes through the points you wanted to pass through. The trouble starts because it may be that the points you're interested in are singular points on the curve you start with, or indeed it may be that they are not, but the new curves pass through the singular point. In fact, they may unavoidably pass through the singular points. And now you have to count how often they pass through the singular points. How do you say how many intersections there are located at that point? Right. This goes back, or was tackled by a very famous theorem of Max Noether's called the AF plus BG theorem today, not letter C actually used, never mind. You have two plane algebraic curves, f and g. So I want you to think of a couple of curves. I'll bring a picture along in a minute. And these curves are polynomial equations in, I've gone projective on you, 3 homogeneous variables. And I want to be able to say that your favorite curve, right, h, is or is not writable in the form AF plus BG, where A and B are also polynomials in 3 variables, okay? So pretty obviously, at points which are common to the curve, polynomial, everything in sight is a polynomial in 3 variables, right? So pretty obviously, if f and g vanish at a point, then h will be equal to 0 at that point. H has to vanish at that point as well. It has to pass through the common points of f and g. And Noether complained that people had assumed that was enough. And here's a very simple example to show that it isn't. Start off with the 2 red curves. One is a parabola, the other is a straight line, and they have a tangent at the origin in common, right? And now if you try and say, well, what other curves are a linear combination of, let Z be 1, y equals x squared and y equals 0, well, you're never going to get y equals x, right? You're going to have an x squared in there, whatever you do, which is to say that any linear combination of the equation of the parabola and the equation of the straight line, because they share a tangent, any linear combination will share that tangent as well. So the sloping line, which I've labeled h, right, this guy here, can't be of the form AF plus BG, although it passes through the common 0, okay? So it's more complicated than that. That was Noether's first insight into all of this. After much struggle from 1872 to 1894, he and Brill get the correct story, not so much for the affine case as the projective case. It took David forever to educate me as to what is harder about the projective case. Okay, this is not kind of, you think, what's the problem, right? I mean, I'm interested in these curves. They meet in a certain number of points. Right, fine. I will arrange that none of them are at infinity. I'm talking, I go down from projective to affine. I take care of the points I can see. They're all in the finite part of the plane. What could go wrong? Okay. Okay, so I don't want you to sort of sweat over this too much. The condition is that at each point where f and g meet, right, there has to be an equation of the form h can be written up to a very high order in the form of a prime f plus b prime g. And because we don't know the order, a prime and b prime are now power series. Okay? That's the condition. What I want you to remember from this is that Noether, Brill and Noether, thought that the fundamental theorem said that if you want to know if your favorite function can be written as af plus bg, you look at the points where the curve f equals 0 and g equals 0 meet. That's all you have to do. Okay? Never mind what the test is. The test is purely local at the set of points where f and g meet. And you knew they were going to play a role in the story, and it turns out nothing else does, they say. Okay, this theorem allowed them to prove their version of the Riemann-Roch theorem. Well, curves will have singularities, and if we're talking about how one curve meets another, or families of curves moving, in the story, you will have nasty singularities. And you can't guarantee that your ground curve doesn't have nasty singularities. Klebsch's formula applied to curves of low degree and therefore low genus. But in general, you might find that these things are rather seriously complicated, and the singularities of the curve you're talking about and the curves that meet it may also coincide. Right? So picture in your mind a very complicated intersection as the basic curve, and then picture another one, and now superimpose them. So one complicated curve is meeting another complicated curve with maybe some tangents in common, maybe not. Right? All of these cases have to be dealt with. And Noether pioneered the view, and so did Cremona, that you could trade this in for a collection of double points. Right? You could go to the complicated points, and today they say blow them up and then blow back down, and you have expanded your nasty singularities into perhaps a bunch of not so nasty singularities, but now several of them. And you carry on doing this, you hope, in a way that eventually calms down, because it's not obvious even that it calms down. So that's what these people believed, all right? So that's the next thing, right? You have a situation, to sum up, where if you want to know if your favorite function is of the form af plus bg, you're all right if f and g cross each other in a nice, simple way. No tangents in common, for example. In this case, the counting argument is straightforward after all, okay? That's the only thing that's really easy. And after that, your set theoretic arguments are going to be quite possibly difficult, and in some cases wrong. So this is where Macaulay kicks in. Decisive thing about Macaulay is he does not say, oh yeah, complicated singularities can be resolved. He says, no, they're there, and I'm going to deal with them in situ. I'm not going to blow them up. And he starts off with geometrical arguments, and he drifts more and more over to algebra. So here's a fairly simple case that will illustrate what a one-set point turns out to be. Your favorite polynomial h is obviously a sum of x to the I, y to the j with some constant coefficients. I've called them aij, okay? So there's your polynomial, these are its coefficients, and you want to know if you can write it like that. Well, pretty obviously, the constant term must be 0, the x term must be 0, the y term must be 0. There are a few coefficients at the start that must be 0 or there's no hope. Macaulay called these modular equations. It's a term he gets from Kronecker, who decided that that was a good way of linking back to Gauss.
Modular equations are the equations?
These are the equations for the coefficients. You have your favorite h. You come to me and say, is it af plus bg for some f and g? And I say, well, we'll have to look at the coefficients, right? Those constraints on the coefficients, which are satisfied by every member, everything that could be an AF plus BG are called the modular equations, right?
Can you go back to
Yeah, yeah.
is it intentional that you don't mention A22?
No, I'm probably being stupid. That would be x squared y squared. No, that's all right. X squared is in, and any multiple of x squared is in. So that's okay. These tell you what can't be in. Okay? Okay.
We're looking at whether the H belongs to the idea
Yes.
generated by
These are the necessary and sufficient, well, it turns out, the necessary and sufficient conditions. Okay? All right. Now, what about xy squared? Right? It can't be in. If it was in, right, then y squared would be in, and plainly it isn't. Okay? So in fact, these coefficients are related. You can't have some of them 0 and some of them not, because there are consequences. Okay? So in fact, all of these are consequences of A12 being equal to 0. Okay? And Macaulay's name for them was they were derivates. Okay, if I say the word derivate again in the talk, that's what I mean. The point is they are all consequences of one of these equations, okay, which tells you that the variety of the ideal x squared y cubed is not only the origin, that's clear, it's a one set point because everything comes from one of these equations for the coefficients, right? All right, this is a ghastly slide. You really shouldn't let people present slides like this very often. Base point is his jargon term for a point that supplies conditions for a curve. Well, your f and your g cross, for example. And it has a degree, which is the number of equations that it supplies. A one set point is like a complete intersection. It tells you everything about the intersection at that point. And a whole base point common to two curves is a one set point. So there are out there, and good intersections between curves, if you like, are one set point. This is 10 pages of technical stuff, and my opportunity to say that Macaulay sketches his arguments, right? And often says, look, this is really rather complicated to write down, but here's a typical worked example, which I urge you to accept as entirely typical. Otherwise, you're going to have surfaces and indices, and it's just going to be awful.
Could you re-explain the first paragraph? This point is a kind of
Okay, so remember we said that if you're interested in curves meeting for any reason, okay, we're really interested in where, if you've got two curves, you're really interested in where they meet. So a base point in the plane is one that imposes conditions on H, your candidate, right?
Yes.
So if the curves don't meet, there are no conditions. You can do anything you like. That's a reasonably simple piece of algebra. If they do meet, then you have to think, what conditions are there? For example, when the parabola met the line. And you will have a number of conditions that are imposed. For example, that if you had the parabola on the line, that your curves, your candidate curves not only had to pass through that point, the origin, but they had to have a horizontal tangent there, right? So that would be two conditions in that case, and that's indeed what's happening here. And then he has a theorem which says that one set points give you the complete information at that point. You can handle it, right? This is not a scrupulously proved theorem. And here's a little bit about what it's good for. So I want you to look, first of all, at the picture on over here. That's what, oops, work on, and then we'll add a line to it. So you've got a ground curve, gamma. I didn't get gamma onto the screen. Gamma is the parabola, right? Gamma is the parabola, right? It meets a curve C1, which I want you to think of as 2 points.
R1, Q1.
R1 and Q1, exactly so. That's the first of the red straight lines, right? So that's the first of the red straight lines, okay? And it meets another red straight line in the same point Q1 and another set R2, Okay, so R1 and R2 have something in common. That is to say that each of them, taken together with Q1, is a complete intersection, right? Okay, so what's this thing Q2 doing up there? Well, again, you can start with Q2 up there, and you can connect it to R1 down there, okay? Does that mean there is a curve through Q2 that connects it to R2? Answer, yes. Now, look, okay, you could have done this at school when you were 15. This is a really shocking picture. And what's wrong about it is that this makes it look like it's obvious. You really have to look at this picture and think that gamma is some very complicated curve, that the red lines are also very complicated curves, right? That they meet the curve gamma in some singular points, perhaps, right? And now you're telling me, well, okay, I can connect Q2 to R1. Why does there exist another curve that connects Q2 to R2? That's not obvious. All these questions about there exists something such that are a little bit harder. It's not too hard. The fundamental theorem does it for you, okay? So you have R1 and R2 are co-residual points, and if they're co-residual with respect to Q1, they're co-residual with respect to anything else they can be residual to. So being co-residual doesn't depend on the Q's, it just depends on the R's.
Just what is the condition on the curve that should go through R2 and
Well, you start off with Q1 and you draw a couple of curves through it, okay? R1 and R2 have this in common, that they are, to get R1 and Q1 are the complete intersection of gamma and a straight line. R2 and Q1 are a complete intersection, right? Only instead of a straight line, you must think of some horrible curve of degree 93, okay? This means that in the jargon term, R1 and R2 are co-residual. They have a residue with Q1. The question is, do they have a residue with respect to anything else? If one of them has a residue with respect to Q2, does the other one? Answer, yes. Which means that being co-residual is, you can make an equivalence class out of it because it doesn't depend on the Q's, it just depends on the R. And if you remember, I said that when you're talking, say, about Riemann-Roch, you have your curve gamma, and you want to specify some points on it, so you pass a curve through those points. The curve you pass through those points is going to meet in some other points. This is the language you can use to handle, and I'm not going to discuss this, to handle the way you get rid of the problem posed by these other points and can count the right dimension, okay? So that's how that figures in this. But please look at this picture and don't think nice, easy things to see. Think things that are impossible to draw, right? That's where the difficulty is, and that's where the whole problem with singular points is. And Macaulay's insight is that no matter what the intersections are, right, no need to blow anything up. No matter what the intersections are, if they are one set points, right, if the algebra determining the coefficients is what I said it was, it all comes from one constraint on the coefficient at that point. If these things are one set points, you can handle how you've got R points and Q points when you come to count them. Even if everything is taking place at one point in the plane, you can divide it up into the R points and the Q points. Nothing prevents that occurring, right? The curves you're drawing through the point you're interested in may curl back and go through it again. And there may be singular there, right? You have these complicated intersections and you want to be able to count the number of times something passes through there, and you can do it if and only if, Macaulay says, they are one set points. And have I skipped? No. So you can do your counting if it's one set points and it's a matter of algebra, okay? Which means that if you've got an R and a Q, right, I can also say, how much, and they're all in one point. I can say how much of it is an R and how much of it is a Q, okay? And not just, oh, it's a complicated point. In particular, therefore, if you have a one set point, you can divide it into 2 bits. You can do subtraction. And if Riemann Roch is about subtraction in a way. It's very hard to describe without giving a lecture course what Macaulay did. But if you think, okay, he took the issue of singular points, he didn't bother to resolve them, he proceeded to analyze them as they come, and he decided that what a singular point can be understood as is supplying equations to the coefficients for candidate for belonging to an ideal, then the way the singular points can be handled, no matter how complicated, no matter whether they all seem to be, everything seems to be happening in one point, when you draw the graphs, you can separate these things out, this bit and that bit. Okay, it's quite an achievement. Okay, in 1904, he's invited to the ICM in Heidelberg. He's not, I think, the only school teacher ever to speak there, but I think we're at the end, or even past the end, of the period when German mathematicians did their time in school, because that's where they earned their money before they could become professional mathematicians. I think the German situation, at least, had become thoroughly professional in something like the modern term. So he turns up and he gives a talk in which he generalizes his work from the plane to higher dimensions. And it's not exactly wrong, but what he proclaims is going to happen is actually not quite right. And so Max Noether comes up to him and says, well, you might like to get this 600-page book and read it, you know. So here it is, probably easier than the 600-page Hungarian version that came out the year before. And you will find in it an extension of Noether's fundamental theorem in a special case of n functions in n variables, okay? Well, you had 2 functions and 2 variables before, so, you know, why not? Okay, if you're going to higher dimensions, this basic theorem, Noether's fundamental theorem, no longer applies, okay? It might, it will in some cases, and it might not in others. Essentially, you just can't just appeal to it, okay? So I want you to look at this rational quartic curve in space, parameterized like that. And yes, I am not missing a term. There's no s squared t squared term. That apparently, according to David Eisenberg, is what makes this thing particularly interesting. Okay. It's simple algebra to see that the curve is cut out by these things here. xw minus yz equals north, the 3 cubic expressions, right? And as a matter of fact, as Macaulay will later show, it's a prime ideal. All right. This is a curve in space. Just think of yourself as having a wiggly curve in space, and you cut it with a hypersurface, so that will give you 4 points, right? Cut by the quartic and the 3 cubics. And the way I've set it up, this hyperplane meets it in these 4 points, okay? Now, if Noether's theorem was true, anything that goes through these 4 points would be of the form a sum of the hyperplane equation and the quadric. Any quadric, at least, would be the quadric and some multiple of the hyperplane. That's all you've got. You've got one thing of degree 1, one thing of degree 2, anything else of degree 2, you're going to multiply the something of degree 1 and add it to the cubic you've got. A dimension count will show you that there's a 5-dimensional space of families of quadrics through 4 points in space. You've only got a 4-parameter family here. Something must be missing. And for example, if you do the baby algebra, this guy passes through those points, but is not of the right form. So Noether's theorem is just false. Okay, that's the first thing that goes. Right? You have to start all over again. If trailer for what's coming next, primary decomposition, if you do the primary decomposition, David has a machine that does that. It's quite hard otherwise. You get an ideal for each point and some other little thing sitting over here which doesn't correspond to any points, actually, but it still has to be checked, right? So this says that your test for membership, your AF plus BG theorem in higher dimensions, is not a matter of going to the points of intersection. There's something else as well, okay? Well, Macaulay doesn't seem to have had a very dramatic life until 1911. He's not the senior mathematics master at his school, he's the deputy. St. Paul's, I should say, for those of you who don't know, and why should you, is a very elite school, okay? Not one of the things we call a public school and anybody sensible will call a private school, but a very elite school nonetheless. There are a few dotted around London. St. Paul's is one, an ancient school, actually goes back to the 16th century. And Macaulay has been the senior, yes, what I want to say, the teacher in the higher reaches, right? Preparing them for Cambridge. 4 of his former pupils went on to graduate top from Cambridge, the so-called senior ranking. 6 of them won the prestigious prize called the Smith's Prize. There's some overlap. 2 of them became fellows of the Royal Society. Actually, they passed through St. Paul's in successive years. That's Littlewood and Watson. Okay, that's a Whittaker and Watson. You know, really, come on. You can't do better than this as a school teacher. Did he get promoted when the headmaster retired? No, he did not. Okay, so he complains, and there's an agreement that, okay, look, we'll give you a generous pension, fine. And it does, I think, you know, what money was then and what money is now isn't clear, right? It's not simple, but between about 70,000 and 110,000 a year, not bad for a retirement income. Okay, and he stays in London for a bit longer, and then he comes back to Cambridge. At this point, we meet Emmanuel Lascar, who is at this stage the world chess champion. He's in New York, a cigar chomping kind of person and rather aggressive over the board. He played the strangulating kind of chess rather than a sparkly kind of chess, but must have had an intimidating presence. And in 1905, so just the year after that ICM, he publishes Zur Theorie der Modulen Ideale in Mathematische Annalen, which is the paper that changes the field. Here's one of his ideas. An ideal can be residual to another. The residual ideal of n with respect to m is the things you can multiply n by to wind up in m. If that's hard to remember, just think of what do you have to multiply an even number by to wind up with a multiple of 6? Well, a multiple of 3. And the multiples of 3 happily form an ideal. So the residual ideal of 2 with respect to 6 is 3, okay? So if I say residual, just think that. Okay, so there are prime ideals. That goes back at least to Kronecker. If you have a product in the ideal, then one of them has to be in the ideal already. Lascar introduces the concept of a primary ideal, and he does it by talking about the corresponding varieties and the points on that, which is fair enough. A lot of this is going backwards and forwards between the varieties and as geometrical objects and the algebra of ideals. But really, it's better if we just jump to the bottom because it's an equivalent condition. If you have 2 things in an ideal and one of them's not in, then a power of the other one is in, you have a primary ideal. And it's primary ideals that correspond best to, for example, the fundamental theorem of arithmetic, right? If I want to factorize 24, well, it's divisible by 2 to the 3, okay? So you need sort of powers of things, and powers of prime ideals aren't quite right. Primary ideals are quite right. So this is an original concept of Lascar's, and he says, we're in polynomial rings, of course, still, that if you have an ideal in a polynomial ring, you can always write it as an intersection of primary ideals corresponding to varieties, and then this weird guy at the end, right? It's there. You just have to realize that this is what rules out checking on intersections. It's there. I'd like to try and give you one example of what it's not so bad. I want you to imagine that you've got your favorite collection of homogeneous polynomials. They were called forms by people times. So you've got your favorite collection of forms, right? And you arrange them in a sequence, the first one, the second one, so on to the end. Right? It's important that they are now in a sequence. And you say, okay, I'll take the first one. What do I get by way of a variety? Well, you know, it's a variety of codimension 1, surely, in the space you've got. And now I'll take my next one. And I'll say, what have I got now by way of a variety common to both of these things? Well, I've got 2 polynomials, so surely it's codimension 2. And I chuck the next one in, and the next one in. And if the dimension goes down by 1 each time, nicely, it's called a regular sequence. Okay? So, for example, if you have f and g in the AF plus bg theorem, you take f and then g, right? And that works, okay? And Koenig's theorem, one of n variables and n functions, is you take a sequence of n forms that are regular, and you just show that the AF plus bg theorem generalizes to them. Okay, and another big theorem of Lasker's, which I've brought along, which says if you have a regular sequence, then that weird term at the end isn't there. Okay? You have the irreducible varieties. Each irreducible variety corresponds to an ideal. Those ideals you take the intersection of. Irreducible varieties give rise to primary ideals. This is an intersection of primary ideals. Okay? It's well behaved. Okay? So I think I might gloss this one. Just think that what you saw corresponds to the best possible case, right? The varieties correspond nicely to primary ideals. There's nothing in the way. Here's another thing that varieties might do. If you think of this as a variety and this one as a variety, there are points on this variety which aren't on this one, and vice versa. So the jargon term is that they are isolated varieties. There's something here which you have to have this variety to tell the whole story, okay? And likewise, there's something that tells you there's an ideal you have to have. It will be a relevant ideal. On the other hand, you know, somewhere in this intersection of the two of them, right, I might have points which are common to both, and I might decide I want them to a higher multiplicity or something. So, okay, but you know, otherwise I've got all the points already. So they are the irrelevant ones in a sense. They're there, but you got them already. You don't need any more ideals or anything like this. And the good thing about Lasker's theorem I just showed you is that the primary components of in a regular sequence are all of the same maximal dimension, okay? So for example, take an example from David's book. You haven't got a plane and a line through it, okay, for your variety. Testing for membership in general is a matter of testing ideal by ideal, and as Macaulay says, that might be no easier than what you originally thought. You've just got an extra ideal to look after, okay? His big breakthrough paper is 1913, so we've gone 9 years since he's been at the ICM. I tried to talk about residuation, these Q's and R's. Macaulay has a way of generalizing it to ideals being residues, one of the other. He has a concept of a perfect ideal, which is very slippery in its first incarnation, at least to me, and overlaps a lot with his early work on the one hand, which I didn't talk about, and Hilbert's work from the early 1890s, okay? Which, to my surprise, it doesn't look like very many people had read, okay? He's, you know, I can't find anything in the Jahrbuch, suggesting that these papers were picked up. Hilbert's work on this stuff seems to have disappeared from public consciousness pretty quickly. There's other stuff listed here in round brackets, which I'm not going to talk about. It's the machine that makes it work, okay? And really, it's pretty scary. We're not that far from elimination theory. And, elimination theory is for consenting adults in private. You don't want to talk about it in public. These things are called perfect ideals, are called perfect because they have good properties, right? Primary decomposition of a perfect ideal is very, very nice. It has a property called unmixedness, which I'll come to later on, okay? Why do I want to mention unmixedness? Because that's the class of ideals which allow you to generalize Noether's fundamental theorem, okay? I don't want to say how, because that's quite a bit of work, but that's the connection back to his early work, okay? The version of Noether's theorem in the plane is fine. It doesn't generalize automatically to higher dimensions. It does if the ideals you're talking about are unmixed, which really means that all the corresponding varieties are of the same dimension, okay? That's what's unmixed about them. The perfect ideals have to do with how many modular equations have you got, okay? And that's all I want to say about it. You can have, the number varies from situation to situation. It was analyzed, as I say, early by Hilbert, independently, but later by Macaulay. You can have only so many of these things, and if your ideal is such that you have the maximum number of independent modular equations, Macaulay called that a perfect ideal. I don't think I've explained that to anyone, okay? You really have to sit down and think, what does this actually say? And it's not a great piece of writing by Macaulay. But what he does say, which is nice, is that if you have a perfect ideal, so M, and it lives inside another ideal, you can, first of all, take the residue, okay? And you can take the residue of the residue, and you get back to where you began. This is like saying you have an R, and you can go to a Q, and you can go from a Q back to an R, and the R's are at least equivalent, okay? That's what's happening here. That's what's being generalized. And in terms of who read this, the answer is, well, actually, Emmy Noether and her people did not. This sat there until 1974, when Peskin and Spiro picked it up. Okay, so this is one of the things that Emmy Noether didn't get. He then, in 1913, wants to know where to publish this theorem in this paper, which is about 100 pages. I think it's about 100 pages, maybe not quite that long. And he thinks, well, mathematics in Ireland's the obvious place, which it is. So he sends it off to Hilbert with it's very strange. I mean, he writes this very defensive note saying, look, you're obviously the right journal, but if you don't want it, I can get it into the London Mathematical Society, no problem. But they will be going to press in about 3 months' time. So I'd kind of like to know soon what you're going to do. Okay, so on the one hand, I don't know if it's good enough for your journal, and on the other hand, make your mind up quickly or I'll go somewhere else, right? And they don't make their mind up fast enough, and he writes another letter, and Klein has to scamper around trying to find a reviewer for the paper, and of course, they take it. Now, in the letter to Hilbert, he says, I've held it back for a while because I want to prove any prime ideal is perfect, and it turns out it's not. And he knows this eventually, and the footnote goes into the paper to say so, and it's our friend, the curve we met before. Okay, you have the details after the talk. Just remember, this curve we met before is another way of saying things are different in higher degree. Prime ideals are not necessarily perfect. Okay, on to 1916, right? He publishes a Cambridge tract. I think these are limited to 128 pages by some decision of the publisher. At all events, as we approach the end, Macaulay starts squashing things together and not doing his usual job of explaining things very thoroughly. The start of the book is English schoolmaster, right? And the end of the book is this and this and this. It introduces the concept of unmixedness, which I'll explain in a minute. He introduces some examples to say that it's worth talking about them. There are things out there. He gives a different definition of perfect and proves that indeed perfect ideals are unmixed, okay? Not the other way around necessarily. And then you have more of this wretched machine, right? This huge thing for doing the work, which again, it's very, very hard to set down in full, and sometimes he just gives difficult examples, and one has to sympathize. An unmixed ideal, bless it, is one whose relevant ideals, isolated and embedded, are all of the same dimension. So every variety you're looking at individually, as you look at the, from one sub-ideal to another, and you look at how this thing is put together, are all of the same dimension. You're looking at, if you're in 3 dimensions, surfaces coming together. You're not worrying about surfaces and lines, or surfaces and curves. So there's no embedded varieties. Or every bit of the story belongs to a specific ideal, and you can't go without that, okay? And a primary ideal is unmixed, he proves, and the corresponding variety is therefore irreducible. Looking at my watch, I think I'm going to skip this. Can we just agree that if you really want to know, I can tell you what a determinantal ideal is. It's a generalization of presenting ideals by taking a bunch of them and forming into writing a matrix of them and taking the maximal codimension things that you can get. And under certain conditions, this gives you more examples of unmixed things. There's a lot of unmixed things out there, okay? So that's the tract. Bad year to publish, 1916, okay? Middle of a war. Gets an interesting review from a French mathematician, one from a short review from an American mathematician. There's a German after the war, and somebody else whom I forget right now. So it actually does get read, okay? Which is important because Emmy Noether is going to pick it up, actually. Over to 1927. This is a paper on these Hilbert numbers. It's one of the papers on Hilbert numbers because it tells you exactly what Hilbert functions can arise. It's remembered in the subject by the people who do it for this. The proof of the theorem, which as presumed earlier, is given only to place it on record. It is too long and complicated to provide any but the most tedious reading. Okay? And of course, naturally, people have swarmed over it and tried to make it less tedious and shorter, and by and large, they've succeeded. But I have to say I like this. I don't know very many examples of somebody saying, I will now give you an unreadable bunch of pages. And by comparison with modern standards of long, unreadable pages, it's quite short. It's only 10 pages long. But there we go. Tedious it is. The next year, he's finally made a Fellow of the Royal Society, proposed by these illustrious gentlemen, including 2 of his previous students, I think, Littlewood. No, not Watson, funnily enough. Littlewood, Hobson at Cambridge, Jeffreys and applied mathematician, McMahon, who's a combinatorialist, Baker, who's here, Hardy, who is, of course, the leading mathematician, Aston and Fowler, and they cite these papers, the 1913, the tract, and these other ones, for making distinguished contributions to the theory of modular systems. There you go. The final paper, 1934, is also interesting. He begins by referring to van der Waerden's Moderne Algebra as the standard work on the theory of ideals. This is the book where the ideas of Emmy Noether and Emil Artin are explained, and the theory of ideals is given in commutative and non-commutative rings. And Macaulay says of it, many theories, at first apparently diverse and more or less independent, have been combined by E. Noether in a wonderful manner as the theory of ideals of rings in general, both commutative and non-commutative. And he particularly likes the Noetherian chain condition, which he calls a more subtle and in some ways more advantageous form of the assumption that every ideal has a finite basis, as is always the case for polynomial rings. He then summarizes the basic features of the theory. This is the first time, to my knowledge, it's set down in English, and he adopts, which is just coming in, I think we have Kroll to thank for it, the set theoretic approach to ideals. Previously, they had looked at whether the corresponding varieties are contained one in the other, which gives you the ideals back to front. Now he decides that, come on, 6 is a subset of 2, right? Anything which is a multiple of 6 is certainly a multiple of 2. He says there could be no better example of the method than Crawl's proof of Lasker's extension of Noether's fundamental theorem, which has not been published as far as I am aware. And this is a key paper in the theory and ring theory. Even Crawl admitted it was in a relatively hidden place, and Macaulay doesn't cite it and seems not to have known it. So there's a question, how did he know about this? How did Macaulay know? We suppose there must have been letters. We can't find any. Our fear is, and has been for years, that Macaulay reads the letters, absorbs them, and throws the printed copies in the bin, right? So I don't think there ever will be letters to back this up. He has some other concepts. I'm looking at the time and thinking I should press on, really. These things called principal systems, which lead to things called super-perfect ideals, which are terrific for residuation and double residuation. And then he says this theorem, if I'm not mistaken, is one of Noether's in general ideal theory. Grosvenor has used it for proving some important properties of ideals. So here's another person he knows about, right? And again, we don't really know what he had read. There may have been more correspondence. These things called super-perfect ideals generalize wisely the concept of one-step points, which are the things which are his sort of first breakthrough, okay? And there are theorems about super-perfect ideals and double residuation, but, you know, getting to the end of the talk. Okay, Macaulay dies in 9th of February, 2 days short of his 75th birthday, 9th of February 1937. And of course he gets an obituary. It is an obituary in the ordinary sense, and it has a reminiscence by Littlewood, who had, after all, been a pupil. This is a very informative little piece by Littlewood. And of course, it being an obituary, there's a bibliography compiled by F.P. White, the editor of the Proceedings of the Cambridge Philosophical Society. The obituary, largely by Baker, is really rather grudging. Right? Didn't really understand modern Italian methods, is what Baker says. False, I would say. And it omits no mention of Macaulay's obituary of Max Noether, so it's not even complete. And more remarkably, it doesn't mention Macaulay's last paper, which White should have known about because it was published in the journal that White edited. Right? This is pretty bad deal, I think. Macaulay's reputation, however, was solid in Germany because along with Lasker, Emmy Noether found these papers really interesting. Lasker more so, I think, in the end, but Macaulay certainly. Obviously, the problem with Macaulay from her point of view was that it's a lot of elimination theory, but the good news is that the details are really, really good. So Macaulay is mentioned in the famous Emmy Noether paper in Ireland about ring theory, the paper in which abstract methods are brought out, and which the ascending chain condition is brought out, and which inspires Van der Waerden and Crawl and others. But that's enough, and I'll stop here.
Thanks a lot for this insightful talk. And I invite questions. David?
So thank you very much, and let's be clear that I have not actually read a line of Macaulay, so that you do not mention more than what I'm saying. But I guess the image from afar is that it's a kind of impenetrable thicket of computations. It's very computation heavy, very difficult, and you made it more intelligible in a very nice way. So historiographically, how far do you feel it is from what he's doing? I guess is the core question. If you reformulate in this a bit nicer way.
Right.
I mean, of course, it's not Noether.
Sure. I think that in the papers up to 1902, it's all plane curves. And what's original is that he's not going to rely on resolution of singularities, which is a pious theorem at best, right? I mean, it's sort of a theorem, and it's sort of, yeah, well, okay? So when Macaulay finally decides that's not good enough, and then he has to deal with the singularities as they present themselves, and so he has to find some way of saying, well, how do we count? And we count by counting the number of equations that we can get from the singularities. Right? That's what we can count. Okay? It might be easy in some cases, it might be very hard in some cases, but we can actually lay our hands on them and we can count them. And then there's a good situation, the one set point, and a bad, but a more complicated situation. And he explores the consequences of the good situation. So that, I think, isn't so bad. I mean, there's always elimination theory bubbling along underneath. I mean, Noether's papers, when you read them, eventually resultants appear, right? And Max Noether has at some point to say, well, I thought my readership would know about these things, but from the letters I've been getting, turns out they don't, so I'll write it again, more attention to what a resultant is. So that's that, I think. And then when he starts in on higher dimensions, so in the tract, for example, the tract is an attempt to, in a way, you know, the tracts are a sort of new readers start here, but it's Cambridge, so we expect you to get to the frontiers of knowledge. And this is a new thing for Cambridge. That's what the tracts are meant to do in a way, is to raise the level. So you have 128 pages, start somewhere sensible and wind up near a frontier. That's the challenge. So 2 chapters, one on resultants and one on the higher dimensional thing called resolvents. So this is pretty technical stuff. And then he goes on to show that, yeah, fine, you do have to use them, but they're not as good as we thought. Right? There are problems with them, and he gives worked examples to show that these resultants and resolvents miss details that he can actually find, right? And that has to do with an ancient question, really. I mean, it does go back to Cramer and Euler, right? You have two equations lying around, they describe 2 curves, you want to know where they meet, right? Now you know this one, right? You all know this one. 2 cubics meet in 9 points. Right? So there's something special about these 9 points because you can pass an infinity of cubics through those 9 points. But in principle, a cubic equation is defined by something of 10 coefficients, 9 ratios, 9 points, or to determine a unique cubic. So there's something funny about these 9 points. The equations they determine are linearly dependent in some way, right? So this is the kind of thing that resolvents do for you, okay? And you kind of churn away at this, and you want some way of working at this in higher dimensions, and the resolvents essentially allow you to project down one dimension and see what's happening there, okay? So this is mainstream stuff. In a way, you could say it goes back to Hesse in Germany, if you like. It goes back in Jacobi. It goes back to Salmon and Cayley in this country, in Ireland. And yeah, right? And it's good for what it does, but he wants to say it's not so good. And once Lasker's paper is out, what Macaulay is really, this is when it gets new, Macaulay is really interested in, okay, I've got the primary decomposition, now what? What can I say about the corresponding varieties? Okay, what am I able to get at now by looking at these ideals that I couldn't get at before? Right? How do I get them in the first instance? Right? So he has sharper questions to answer, and you can think of Lasker as a real turning point, actually. The Noether route out of Lasker is the abstract stuff. The Macaulay route is the more specific, concrete stuff. And of course, Emmy Noether, being top class, thinks, actually, you know, the detailed stuff is really important. We really can't forget that, okay? Although I don't suppose she was going around saying that's the right way to do it, but those things. So I would say that was kind of, does that answer your question in a way? I mean, that's the tradition into which this fits, and that's the novelties that these people bring to it, right?
Okay, just to stimulate further discussion, I would like to return to a point, something that you said that struck me because I would like to understand better what you meant when you said shifting from variety to set.
Mm-hmm.
How do you interpret, how do you understand this shift? I'm very interested because it seems to me it relates to something we were discussing.
Right.
So could you comment on this?
Okay.
Of the sentence, because you said it.
No. I think, certainly for Macaulay, but I have the impression for all of these people in a way, you know, what are we really talking about? We're not deep down talking about polynomials. Those polynomials represent something. They're the carriers of something that's interesting. Those things are the shapes, the curves, the varieties, right? You can really think that's important, as Macaulay did in his early days, and various people responding to the Noether fundamental theorem did. Right? We're really talking about these curves, right? As it happens, we handle them by equations, right? If you want to have more variables, then we're talking about varieties in higher dimensions. And, you know, there was a time when the people Macaulay read were saying, if only we could understand how these things intersect, we'd have done it, right? So there are transverse intersections where they cross, the tangent directions are all different. And then there are more complicated ones where some of the tangent directions are shared, okay? So that's what we have to elucidate, right? Is this geometrical stuff. And Macaulay starts to say, no, just forget that. It's just algebra, right? So with Lasker, what you see is a kind of, I don't want to say duality because that's such a technical word, but you have these shapes, these varieties, and you have these, well, we call them ideals. And the ideals have this, you know, there's this wonderful fact about ideals that they are primary, and you have a primary decomposition theorem, right? But you still want to go to the variety, for example, for the definition of a primary ideal. The question of what shape is it talking about, right? Where does that, what are the shapes here somehow? So that's the fundamental thing. So if my variety is a subvariety of yours, right, your ideal will be a sub-ideal of mine, right? Oh boy, the chances David and I had of making a mistake at any one stage were very high because it's backwards from what we want. So all I was saying was there comes a point, I think probably around about Kroll's time, where they say, look, forget this variety stuff, right? You know, the ideals, like, right, they're sets.
Okay, I had completely misunderstood what you had said. And in fact, when you were saying sets, you meant ideals.
Yes,
Okay.
but also it's set theoretic conclusion that you
Yes.
use now, and not
Okay,
something
okay,
that's,
okay,
you know,
okay.
variety, the sub-variety. Yeah.
Joe.
I have a related
Joe, hi.
question that goes back to something you said at the very beginning of your talk, and it relates to the things we've been talking about the last couple of days about problems of translating from one language into another, and what happens when you go from, say, German into English, or using words that seem similar but may have very different nuanced meanings in the original German from what you get in English. You said, well, you know, what they were talking about as modules, we understand as ideals. So to not confuse the modern reader, we're calling them ideals, because modules would give you another interpretation. We use that word for differently now. But in calling those ideals, modules, how much are you overly precising what they were having to deal with, and we're really having trouble struggling with, when you now call them, well, we understand those as ideals?
They have exactly the definition that we have. Right? You know, that's a straightforward, fairly simple thing, right? So to that extent, it's not too dishonest, and it's a new word. I mean, the reason I'm hesitating is, of course, Lasker also introduces something called ideals. Let's not go there. So you're working over the integers rather than over a field. But keep quiet about that. Okay. So I think what you're pointing to is, here's the German word, here's the English word. Each of these things have a cloud around them of association, right? And other, yeah, let's say association, right? And if I take this word in German and I say, in English it's this, the associations may not map one onto the other, right? This one may have other associations entirely, and we risk being misunderstood. But I think if you're bringing in a new concept, right, altogether, and I choose to call it, I don't know. I don't know how these people think of names for things, but well, okay, ideal. I don't think there was any particular sense in either language of striving for virtue and being a, you know, Sir Galahad, as it were, to take a myth from both languages. I think it just was a nice collection of things, right, in each case. And if we use module, I really think, on the other hand, the modern reader would endlessly go, oh no, history, damn it, it's an ideal. Can I think of, I should have come here 2 days ago, shouldn't I? Can I think of examples where this is really tricky? I'm sure there are lots. I mean, there are words which are very strange. In physics, definition of work is one. Energy is a very slippery concept. I think Jesper's going to tell us something about function being a tricky thing, and it's even a strange word, right? I mean, you know, the function of this microphone. I don't feel bad at the end of the day with this particular translation, really, because I think that, yeah, I've said my bit. I have no great illumination to share, just humble.
Well, it's a problem we're all dealing with this week in terms of these questions.
Yeah. But I think, you know, in the end, it's maths, right? We're not writing poetry. If we were writing poetry, well, you'd have to worry about ideal in both languages, right? I don't know. That's, yeah.
I would like to return to something, a question you asked about how Macaulay could know about a paper that had been published in the Sitzungsberichte
Heidelberg.
Heidelberg.
Mm-hmm.
I was wondering, it was at the moment when he was at the Royal Society.
Mhm.
Would the Royal Society buy or exchange? The
Well,
report
that's
from-
entirely possible, and we can go to the UL and see if it had that journal at that time. It would be like Macaulay to say if it was in print, I think. The fact that he doesn't makes me think that he's corresponding with these people. And the way he writes about it, the value judgments he makes in the course of writing about it, makes me think that, okay, the Noether paper is a real thing. That's a big change. But yeah, I mean, you're right. And I should go and check just in case that's how he did it. We've got some, I don't think he's going to go to London, even though you can comfortably by train. He might just try the UL here and see if they had these things. Yeah, it's a question. I agree, it's a question.
No, it's just
But on the other hand, I think these people were probably in touch with him. And that's my hunch. Feels difficult to establish. But
letters?
no,
that's
Macaulay is terrible for letters. There's about half a dozen. There's 2 to Hilbert and 1 to Klein. There's 3 or 4 to Lama about something else. June found 1 or 2 for me about something else. And that's about it. This is a man who throws away letters, right?
Those who throw their mails away.
No. Keep your emails. That's
I
right.
know that
Well.
will be a historian at some point saying.
There are letters in the 2 directions, so maybe we have.
I wonder about that. It doesn't seem much from Kroll either. Yeah, I don't think it's Kroll archives. Is anybody an expert on the matters Krollian? I don't think there is particularly a Kroll archive. So things got destroyed in the war, of course. Okay, I'll have a look. But that'd be great. But you have a catalogue of catalogues for letters, and it all doesn't show up in that. Right. Okay. Good.
Any other question? So perhaps now that we have the sun, believe it or not, it's time to thank Jeremy